always, Mohammed Hassan says that what is the broadcast address of a network? If you look at the address, an address consists of two sections, and a subnet ID and a host ID part. Okay, forget the subnet ID. It's related to, it's similar to family name, but we have some bits in the host part of the address. If you put 0 to those bits in the host part, if you put 0 to all of those bits into all of those bits, the result is the network address. And if we put 1 into all of those bits in the host part, the result would be the broadcast address of that network. We cannot change the subnet part of the address. That part is fixed. Just we change the value of bits in the host part. Is it okay? Okay. Any other question? Okay. What is host ID? Mohammed Hassan. My name is Hussein غفاريان. Okay. Hussein is my host ID. غفاريان is my subnet ID or net ID. Subnet ID or net ID are similar together. Okay. But my name is my host ID. We have a big network. It's clarified net ID or subnet ID, but each of the systems in that network needs a specific host ID. It's similar to my first name. More questions? Topic of node routing? What do you mean? We have a subnetting and a supernetting. Subnet or supernet. We talked about these items. What do you mean by node routing? Mohammed Hassan. Mohammed Hassan Shanshul. What do you mean by node routing? I think you mean something else. Okay. Name say, does the DHCP do the main functions of the router? No, Naiman. It's not. If my router is placed at the edge of a network, an access network, I'm in an access network, I'm connecting to the internet through my access network. In my access network, I need a DHCP server. And mostly routers have these services. This service, DHCP service, mostly. You can run a DHCP server in a computer. It's not important, but mostly we run this service, this DHCP service on the edge router, the router placed at the edge of my network. But inside the internet, in the core of internet, we never use DHCP services. Why? Because the routers in the core of internet always connected to different systems. So they need static IP addresses, not the dynamic ones. Okay? So we only use dynamic IP addresses at the edge networks for the systems who are temporarily connected to the internet. For example, I'm connecting to internet, so I need an IP address, and after the class I will disconnect my computer. Okay. No, Mohammed Hassan, can you repeat your question again? I think you rewrite something false, something wrong. What does naturality mean? I think you talk about this section here. Here, okay? I think you talk about this slide 88. Is it okay? You mean talking about this one? What does it mean? Naturality. What does this means? Look at this. We have a network, and we want to use this network for our works in our life. But until now, we learned that when we talk about internet and computer networks, we have to be clear about technical issues. For example, an ISP needs to create some routes, prepare some routes for me, allocate some resource for me, prepare IP addresses for me, manage the traffics in the network, and something like that. Also, we know that everything should be economical. Should be economic. Why? Because it's a business. I'm talking about a business, so everything should be economic in a network. And also, people's today's people use computer networks for their social interactions. For example, they want to talk each other freely, completely free. Okay, we should protect this conversation. Also, we need to prepare a competitive environment and something like that. And also, from the government side, we have to accept some rules in our region. For example, I'm in Iran, so the government of Iran forces me to accept some rules, some policies. Okay, I have to accept them. So although we talked about a computer network, we have to be clear about these issues, technical issues, economical, social, and rules and policies and something like that. But here in this course, we never think about these issues. We never think about them. We just talk about the basic nature of a network. Currently, I'm talking about your question, Mohammed Hassan. Again, I'm repeating again, Mohammed Hassan. You know, there are several issues related to the computer networks. For example, technical issues, social issues, economical issues, rules and policies applied by the government or international organization and something like that. We know that these issues are important for us in computer networks, but here in this course, we never talked about them. We just talked about the basic concepts in a computer network. We just talked about this, the basics, the basic items. Here, we don't care about the other issues, such as technical or economical or social or legal issues. Okay, we just talk about the basics in a network. Okay, is it enough? Mohammed Hassan, is it enough? You're welcome. Any other question? Okay, today we will start talking more about IP protocol or Internet protocol. During the first part, we talked about the format of a datagram packet, and then we talked about addressing issues, and now we want to talk about, and after that we talked about network translation. And today, let me pass this slides. Oh, okay. Yeah. Today we want to talk about network address translation. Okay. When we talk about IP version 4, IPv4, we can see that we have some limitations in related to the number of available IP addresses. So scientists decided to move and migrate to IP version 6. IP version 6 has 128 bits length. 128 bit length. Okay. IPv4 has only 32 bits length. Four times differences between them. Okay, but we know that if I start, for example, today to change the IP addresses from different systems, from IPv4 to IPv6, we have some limitations. We cannot do this migration from IPv4 to IPv6 just in a few days or a few months, and even in a few years. Scientists knows that we have major issues with limited number of IP addresses in IPv4. Okay, and they cannot apply new IPv6 addresses to all of the devices in the internet. Okay, so they decided to make some modifications and some other methods and ideas. They apply some other ideas to solve the problem. The final position or the final goal is using IPv6 in the whole of internet. The whole of devices should accept IPv6. Okay. They start from 1990s, 30 years ago, and still we have lots of devices that they have not IPv6 IP addresses after 30 years. Okay? But one of the proposed methods to solve the problem, limited number of IP addresses, valid IP addresses, is using the NAT address. Is using the NAT services. What is NAT? NAT is network address translation. In this service, we have a personal network here, for example, a network, a home network, an organization network, something like that. Okay, we have a private network. The devices in this network has a specific range of IP addresses. Okay, but in the edge router, I'm starting a NAT services. With this NAT service, I'm translating the addresses inside my network into a new address. Why? Because I have not enough number of valid IP addresses, IPv4 addresses. Okay, I have not enough valid IP addresses. So just I can prepare a few IP addresses, and look at this. If I want to connect to internet, I have to use valid IP addresses. I have to use, but I cannot prepare enough IP addresses. For example, the university has, for example, 4,000 systems. So I need 4,000 IP addresses. I cannot prepare those addresses. Just I bought a few valid IP addresses, and then inside my network, I'm using some special IP addresses. Okay. For example, here you can see the whole systems use IP address range starting with 10. 10, for example, 10.0.0.1, 10.0.0.2, 10.0.0.3, something like that. Okay. برو في کارت کلاس برو بیاد کلاس چی شد؟ حبله. Oh, excuse me. Wait a minute, please. Okay, so I'm using a range of invalid IP addresses in my network, and at the edge of my network, in the router, I'm running NAT service. The NAT service will translate my invalid IP addresses into a valid address or into a valid IP addresses. There are several options here. I can translate the whole of my addresses into one valid IP address, or I can translate my internal IP address into a bunch of different valid IP addresses. Okay, so using this strategy, I'm changing, inside my network, I'm using a bunch of invalid IP addresses, but at the edge of my network and using the NAT service, I'm translating those addresses into a valid or into some valid IP addresses, so I can transfer the packets over the internet, because in the internet we need valid IP addresses. Okay, here in this case, for example, I'm using, you can see, I'm using the range of IP addresses started with 10.0.0.1. Okay, we have three specific ranges of IP addresses in IPv4, range of 10, range of 172.16/12 and 192.168/16. These three ranges, we call them as private IP address spaces. It means that, for example, now I'm in my home, okay, and I'm connecting to the internet through my modem. in the modem, if I check right now, I can check my IP address. Just if I'm using Windows, so just I use ipconfig command in the command line. Okay, just I'm typing ipconfig, and I can see that okay, my IP address is 192.168. For example, let me check. One 192.168.1.100 ipconfig. Write it here in this case. Okay, I'm using this range of IP addresses inside my network. But when I'm going outside of my network, I need a valid IP address. The ISP can set it for me. Hello. What is the difference between a valid IP address and invalid IP address? There is no special differences between them. Okay, there is no special differences. But we know that if, for example, I use the range of IP address 10, for example, 10/8 or 192.168/16 or something like that. These private ranges, okay? I should be clear that someone else can use these addresses too. It means that I'm not the only person who uses these ranges. I'm not the only person. So the difference between a valid IP address and invalid IP address is this. When I bought a range of IP addresses, it's dedicated to me. I register my range of IP addresses, so it's dedicated to me. No one can use my range, okay? No one. But when I use a private range of IP address, I know that I can use it and you can use it too. My neighbor can use these ranges too. But the primary goal of IP address is this: creating a unique address for a device connected to the internet. When I bought a registered range of IP addresses, I'm sure that my range is registered and nobody can use it. But when I use a private range, I know that I can use it and you can use it too. So it's not unique. So if I use a private range of IP addresses over the internet, the routers cannot define the correct path to my computer, because all the users around the internet can use those private ranges. So the router cannot decide about the destination path. This is the difference between a valid and invalid IP addresses. Okay? So we can use these ranges inside our network. But at the edge of our network, we have to use a NAT service to translate those invalid IP addresses into one or a subset or one or a bunch of valid or registered IP addresses. But when we use a NAT address, there are several advantages. One advantage is that in this case, I can use, for example, one IP address instead of using a bunch of IP addresses. Just I need one IP address dedicated to the whole systems inside the university, for example. Okay? One IP address for all devices. The second advantage is that I can change the range of my network. Message says that why change the IP address in router? Because my private IP addresses are not unique. I can use them and you can use them too. So they are not unique. Over the internet, we need unique IP addresses. Unique means that you cannot use my IP addresses. Not you, no you, and no other people. Nobody can use my IP addresses. So my IP address is unique. And you can find, the routers can find a route or a path toward me. This is the basic of this change. But yes, not for safety, for security. For security, you can use NAT services for security. Why? Because nobody knows about your network structure from the outside of your network. Your internal network is invisible from the internet. Okay, it's very good. It's a security strategy. But there are several other issues, several other advantages. For example, you can change your internal range of IP addresses, or you can change the ISP. Your ISP can change his ranges of IP addresses without affecting your internal network. Okay? Okay. For example, let me look at this example here. I'm passing this slide because I want to talk about it here in this slide. Okay, in this slide, you can see that, for example, a host with IP address 10.0.0.1 decided to send an IP address to destination 128.190.40.186 with port number 18. It decided to reach to a web service. Okay, the packet is transferred over this network and it arrived to the router. In this edge router, I'm running a NAT service. In the NAT service, I have a NAT translation table. The NAT service receives the packet and it finds that, okay, there is a packet comes from IP address 10.0.0.1 with port number 3345. Okay, and it translate the NAT service, translate this IP address into this one, 138.76.29.7 with port number 5001. Okay, it just translate this range. So my NAT service translate the IP address, the income IP address, into a new one. And look at this packet here. It replaces my old IP address 10.0.0.1 with port number 3345 into a new one, into a translated one. Look at this. The source IP address has been changed. And then this packet with this valid IP address is sent over to internet through the destination. Okay, the destination will answer me. The destination will answer. And look at this. The destination address is my translated one. Here, look at this. The reply is arrived. The reply of my question, my request is arrived, and you can see the IP address and my port number is registered in the reply message. Again, it arrives to the edge router. The NAT service will check the IP address. It finds this. The IP address 138.76.29.7 with port number 5001 should be translated into 10.0.0.1 with port number 3345. Just it translated it again to my primary IP address. And now the translated packet is sent over my network, inside my network, and it will receive to the correct system. Okay, here by this example I show you how a NAT service works. How a NAT service works. Here you can follow this instruction. If you use Cisco devices, you can see two expression here. One of them is PAT and the other is NAT. PAT or NAT. Cisco uses these terminologies, PAT or NAT. PAT or port address translation is something similar to NAT. when we translate a bunch of invalid IP addresses into a bunch of valid IP addresses, Cisco says, okay, you are doing NAT. But when I'm translating a bunch of invalid IP addresses into one valid IP address, into a valid IP address, Cisco says, okay, you are using PAT. Why? When I use only one valid IP address, in this case, the NAT service, my NAT service, have to use one IP address for the whole packets. But to make it clear which of those systems sends this packet, in PAT, we use different number of ports. We have too many ports, port numbers, okay? More than 65,000 port numbers. We have more than 65,000 port numbers. So simply I can use one IP address and use different port numbers. And Cisco says, okay, if you use this strategy, it's not NAT. We call it PAT because you are using different port numbers. They called it PAT or port address translation. But here, we only say NAT. Okay, so we use NAT because routers works on layer 3 and we have some shortage to use Ipv6 in current systems, but we have to use a NAT service in our network, in a dedicated server or using NAT in the edge router, I don't know. But in today's network, most of networks use NAT strategy because of its benefit for safety, for security. Okay. My router knows the IP addresses in the network. For example, it runs a DHCP service. Okay, so it knows the ranges of IP addresses inside my network, and now it used its knowledge for NAT services. For NAT service. But never, look at, be aware about this. Never a router knows who is, for example, PC1. It's not important for router. He can learn. The router can learns about the PC identities. Okay, it can learn. But mostly the router does not care about this. Why? Because just, for example, in a NAT service, just he needs to change one IP address to another one. Who is care about the source of that packet? Just need to change an invalid IP address into a valid one. Nothing more is necessary. Okay? But if know that if you forget this, the security advantage of NAT, we know that NAT and other strategies like private IP addresses and other proposed method were only temporary solutions, and the final goal is using Ipv6. Why? Someone says that say that if we use Ipv6 in our real world, we can assign unique IP addresses to each molecule in the universe. One dedicated, one unique IP address to each molecule in the universe. That is interesting. Why? Because the length of IP address version 6 is 128 bits. It's too long. So I can say that forever we solve the problem of limited number of IP addresses in our real world. Also, there are other motivations in Ipv6. For example, the header of Ipv6 packets became simpler than header of IP packet version 4. So we can process header of IP version 6 faster than IP version 4. Faster than headers of IP version 4. And there are some other benefits too. For example, in IP version 6, we have used the concept of flu, which is important for quality of service in the network. Look at this header. The header of IP version 6 is something like this. A version, priority, flu label, payload length, next header, hop limit, and source and destination address. That's the whole thing. A fixed 40 bytes of header. But let me again let me show you the header of IP version 4 here. This is the header of IP version 4. In IP version 4, the length of header can be a number between 20 bytes to 60 bytes. And you can see there are several different fields are in the header of IP version 4. Wait a moment, please. Excuse me, wait a moment. So, excuse me for the interrupt. So, when we look on the structure of the header in IP version 4, we can see lots of fields in the header, but in IP version 6, look at this one. here. In Ipv6, you can see the structure of IP header becomes simpler, more simpler than Ipv4. And this simpler format can help the routers to process IP packets faster than previous. It's very important. We need a simpler structure for faster processing, faster packet processing inside a router. Here you can see the source and destination IP addresses are 120 bits length are addresses, okay? And just a few number of fields are in this format. The first one is version. The first field is version, which is number 6. Then you can see priority. Priority is used for quality of service. If my packet, my service has a higher priority with respect to the other traffics, so I can use this priority field to make it clear. Okay, this packet has priority over the rest of packets. Okay. And the third field is flow label. What is flow? Flow is a bunch of packets, a set of packets coming from a similar source, moving toward a specific destination. So those packets with specific source and destinations should be treated similar together. We should act on them. We should process them similarly, same to each other. Their path should be similar. Their processing should be similar. Everything should be similar. So instead of looking for their addresses, source and destination address and rest of the fields, instead of that, just I put a flow label into my packet. And the router checks this flow label. Instead of checking the destination address, it checks the flow label. It's something to circuit switching strategy. Okay? Just it checks the flow label and the router can decide, okay, what should I do with this packet? Just according to the flow label. So this flow label can help me to service better than the primary strategy in the network. The first field is payload length. Here, how much data is carried on the payload in byte, and next header and hop limit. Hop limit is something similar to TTL or time to live in IP version 4. Okay, we have a TTL or time to live in version 4, and in version 6 we have hop limit option, hop limit field. They are similar together. And to get this, we have a specific field here. Its name is next header, next HDR or next header. What is this? In IP version 6, the scientists decided that if a packet needs more processing, for example, a packet needs security options or something like that. Okay? If a packet needs more processing, we put those information into a next header. The next header is put it here in the first part of payload. For example, in IP version 4, we have to run Ipv6 protocol separated, completely separated from the IP packets. But in IP version 6, I can run Ipv6 inside my computers, inside IP version 6. Okay? And to do that, I'm using a next header option. So another header is placing here in the first part of payload. But I know that the Ipv6 header must not be checked in the router along the path. So just a few routers must check the Ipv6 header. We put it as a next header, and just a few routers may check it, not the whole packets. All the routers inside the path just check these first 40 bytes. The header is fixed. The header of our IP version 4 was not fixed, but here the header of IP version 6 is fixed. Fixed 40 bytes. And also you can see that here. For example, here I have not checksum option, I have not fragmentation and reassembly options, and some other options. Checksum and fragmentation fields are removed in IP version 6 because they are not necessary. They just apply processing overheads to the routers. They are not necessary, so they are removed in IP version 6. So I received a simpler version of packet header in IP version 6. But one main question, okay, IP version 6 is very good, I know, it's the best, I know. But I have a computer, this computer cannot support IP version 6. What should I do? It only learn and know IP version 4. What should I do? How can I transit IP version 4 packets over the IP version 6 areas, or in reverse, IP version 6 packets over the IP version 4 areas? What should I do? How can I transfer those packets over the other area? I do. And I know that even inside the network, I know that some routers, some switches, some network elements are inside the networks that I cannot update them. I cannot update them. What should I do with them? Because so in today's network, we have a mix of IP version 4 and IP version 6 systems inside the computer networks. Okay? So the one main strategy is using tunneling. It's one of those strategies. Tunneling is one of the best strategy to solve this problem. If I want to move, for example, an IP version 6 packet over an IP version 4 network, just I can put the IP version 6 datagram inside an IP version 4 datagram. And if you remember in the past, I said that we called it tunneling, putting one packet inside into another packet. Okay, we call it tunneling. So simply I can use tunneling strategy. And in today's networks, especially in 4G and 5G networks, in cellular networks, we use this strategy extensively, broadly, this tunneling strategy. Why? Because especially in cellular network are not computer networks. They come from telecommunication area. So simply we can use tunneling strategy. For example, look at this one here. I have a version, Ipv6 here, Ipv6 network here in the left, and another Ipv6 in the right. But in the middle, in the center, you can see there is an Ipv4 network. And now, if system A decided to send a packet to system F, the packet should transfer over this Ipv4 network. So along the path, I'm using this encapsulation or this tunneling strategy. And my packet along this path, my packet is encapsulated into a Ipv4 packet, and it can pass this area, this network, from here, from system B until F. I'm creating a tunnel, transfer the packet, and on system AE, I can remove the tunnel and extract the Ipv6 packet, and it can be sent over the network through the system F. Why does Ipv4 does not disappear from networks? It's a good question. Naim asked me a very good question. Why? There are two answers. The first one is that I cannot make force the first answer is that I cannot make force on the people around the world to change or update their old devices into a new Ipv6 device. I cannot make this force. Okay? So we need time for this upgrade, for this change, and moving toward Ipv6. And the other option, the other answer is that in some countries, some administrations and some managers think that in Ipv6 there are several potential options which they cannot handle them, they cannot manage those options. For example, in Ipv6 we can use Ipv6 protocol inside the heart of Ipv6. But in Ipv4, I need to dedicate a separated system for Ipv6 protocol in my network. So there is a security issue in this protocol. Because, for example, an intruder, a hacker, and a spy can send, for example, secure message through the network just simply using Ipv6. Okay, so because of this problem, we need to spend more times to remove Ipv4 completely from the word. Okay, how we can apply this one here? Okay, in this case, in tiling, I said that I can put an Ipv6 datagram inside an Ipv4 datagram and send it over the network, and in the other side, I can extract the primary packet, the original packet, from the tunnel. Okay, but there is another option too. If you are looking for migrating, for sending packets over an Ipv4 network, there is another option too, which is translating packet headers from Ipv6 to Ipv4, and in the other side, translating Ipv4 packets into Ipv6. Okay, we call it dual stack strategy. Dual stack strategy. In dual stack strategy, here the system B and system E must know both Ipv4 and Ipv6. So we call it dual stack. Stack of Ipv4 and stack of Ipv6. Those systems must be dual stack, and then system B translated the header of Ipv6 information into Ipv4, and in the other side, it again, system E translates the header of IP packet 4 into packet 6. Okay. If you use dual stack strategy in our networks, we should. It's simpler than using tunneling, because look at this one here. This one. This is a tunneling strategy. I'm putting the Ipv6 packet into the heart of Ipv4 packet. Okay, you can see in this case I'm sending an overhead data over the Ipv4 network. Okay? I'm sending more data over the network, and finally at E, I'm extracting the original packet. But if I use dual stack strategy instead of tunneling, if I use dual stack, it's not necessary for me to send more data, something like this. But we should be clear. For example, in Ipv6, I have a field of flu ID. But in Ipv4, we have not this item, this field. So if I use dual stack strategy, I will lose full label. I will lose full label if I use dual stack, because I haven't full label in Ipv4. So I will lose if I use dual stack strategy, but it's simpler than tunneling, because I don't need to add extra overhead to to the packets. This one is very important, this chart here. This chart is about Ipv6 adaptation. It shows that between January of 2010 and January of 2020, in a 10 years period, you can see most of computers and systems in our world tries to move toward Ipv6. The Google predicts that something about 1/3 of clients who access to the Google server using Ipv6. Only 30%. And the NIST is an organization. The NIST predicts that only 1/3 of US government domains are Ipv6 capable. So still need more time. At least I think at least 5 or 10 years. We need 5 or 10 years to remove the IP variant 4 strongly. So we need a long time. Still, we need a long time for deployment. We spent 25 years. You can see these statistics are the statistics after 25 years. The starting to move toward Ipv6 the starting point was about 1995. Okay, 25 years ago. We start this as from 25 years ago, and still we need to spend more years to this. But how we can solve it and how we can tolerate this process? It's simple. With some application level changes. And because of those application level changes, we tolerate this. For example, you can search for tunneling strategy of Microsoft tunneling strategy for its applications on Windows. There are several application level changes during these past 25 years who helps us. But we still we need more times to complete this way. Okay, that is enough for today. Is there any question? Any question? We will talk about the time. Naima, we will talk about the time of exam. Maybe some students say, okay, a sooner exam is good. Okay. Okay, please, we will talk about the time on our WhatsApp group. Okay. Okay. I wish the best for you during the remaining hours of this day and the days of this week. Okay? Have a good day and goodbye.